All right. Today we're going to continue on in section 8.3. So in 8.3 we're talking about applications of vectors. And the first thing we're going to do is introduce the concept of the projection of one vector onto another. So let's say we have some vector here that I'm going to call V. And then I have another vector here that I'm going to call U. What I'd like to do is I'd like to find a way to rewrite vector U in a linear combination form, but without using the vectors I and j. I'd like to use another vector that's in the same direction as V. So what I'm going to do is I'm going to project vector U onto vector V. So this vector here is called the projection of vector U onto vector V. Okay. So this vector here, I'm going to call W. Notice the way that I've drawn these three vectors. What can I say about these three vectors? Okay, what vector operation is represented by this triangle? This is addition, because I've written the vector, the projection, and vector W head to tail, and then U is drawn from the initial to the final terminal, right? And what can I say about these two vectors, the projection vector and W? They are orthogonal. Look at the picture. What does orthogonal mean again? They meet at a 90-degree angle, which is exactly what we've drawn in our picture, right? Okay. So the idea here is I have vector U. I want to rewrite vector U as the sum of two orthogonal vectors. One of those vectors I want to be in the same direction as this vector V. The way I do that is I'm going to project vector U onto vector V. That's this. In conjunction with this vector W, those are two orthogonal vectors whose sum is vector U. What I've done is I've broken vector U up into the sum of two orthogonal vectors. So let's give ourselves a formula on how to calculate this projection vector, right? Because right now all it is a picture. So if we have non-zero vectors, U and V, the projection of vector U onto vector V is going to be the dot product of U and V divided by the magnitude of V squared times vector V. I'm sorry, can you say that
In
again?
the beginning of the formula, is that like the projection of u times u?
So that's the projection of vector u onto v. So the subscript is what vector you're projecting it onto, and the regular script, inline script, or whatever you want to say that, is the vector that's you're projecting. Okay, so like v is the destination, and u is the vector you're putting in, projecting onto that destination. Does that answer your question, Andrew?
Yeah.
Okay. Yeah, so the v is a subscript, the u is regular inline. If you want to put like a parenthesis around it or something to make it look more like an operation, you're welcome to do that. That's not incorrect notation. If that helps you, you're welcome to do that sort of thing. I probably won't, because it's not really standard, but it's not incorrect. Okay? So let's look at this fraction right here. Okay? What kind of a result is the dot product divided by the magnitude squared going to give us? Is that going to be a vector or a scalar? That is going to be a scalar, right? The dot product is a scalar, and the magnitude is a scalar, and scalar over scalar is a scalar. What is, and vector v is obviously a vector. So what do I call it when I do a scalar times a vector? What's that operation called? That's just scalar multiplication, right? So what this projection is doing is it's just scaling vector v so that you can make it an orthogonal component to u. That's all we're doing, is we're just doing scalar multiplication on vector v. That's going to scale it, shorten it down or stretch it out so that it can be an orthogonal component to vector u. Okay with that idea? Let's do a numeric example to kind of help solidify things, okay? Let's say we want the projection of vector u onto vector v. So this is the formula we're going to use. To use this formula, I'm going to need the dot product of u and v. And I'm going to need the magnitude of v squared. Well, that's pretty nice. The magnitude squared, the squared just is going to cancel that square root. So that projection vector is really just going to be 14 over 52 times 6 over negative 4. And when I do that scalar multiplication, I'm going to have to reduce some fractions here, but I get 21 over 13 and then negative 14 over 13. Yes. What do you mean, will you have to? You did in the homework.
Yeah, but like, would that be fair game for the test?
I mean, at this point, yeah, but I haven't written the test yet.
Yeah. You consider not doing it. It's a side question.
I say our test is.
No, you can. Can we just do orthogonal? Can we just prove orthogonal?
Wait, is that like a C in this division? What's that? It's a 6.
That's the number 6.
Oh.
Thank you for asking. Is everybody okay with how I got to 21 over 13 and negative 14 over 13? Okay. So what I'm going to ask then is, what I'm going to ask you to do now is to write that vector u as the sum of two orthogonal vectors. One of them is this projection of vector v onto u or vector u onto v, which we just found. So the idea here, what I'm going to use is this formula that I wrote down earlier. That u is equal to the projection of vector u onto v plus w. We know what vector u is, correct? That was the vector 3, 1. We know the projection vector. That's 21 over 13 and negative 14 over 13. And now we just need to find vector w.
What were the points of that?
6 and negative 4. So how am I going to find w? Yeah, I'm just going to subtract this vector from both sides. So 3 minus 21 over 13 gives me 18 over 13. And 1 minus a negative 14 over 13 gives me 27 over 13. So there's my w. So I can then say u is equal to my projection vector plus that w vector oops. Oh no, that's right. Any questions so far on what we've done? Okay. How many of us are in a physics course right now? Just a quick show of hands. Okay. One of the nice applications to using these vector projections is dealing with some physics problems, particularly force problems. And one of the more difficult first semester physics problems you'll do or deal with are situations where you have forces being applied at angles. And these are types of problems that can be quite complicated. but if you handle them with a vector projection, become, I think, considerably easier to set up. So let's look at an example. So, Kyle is going sledding on a hill with a 25-degree angle of incline. Kyle and the sled weigh 165 pounds, and we're asked, what is the amount of force moving down the hill? Okay. Those of you that took physics already, either are currently taking it or took it last year, this should sound like a familiar kind of setup of a first semester problem, right? Well, we're going to do it differently than they would have done it in their physics course. So there's no real big advantage. So the first thing I'm going to do is sketch a little picture. So the first thing I'm going to do is draw a vector for the hill. So I'm going to call that vector H. Because we're going downhill, I'm going to draw my vector like that. And it says the angle of incline is 25 degrees. So I'll draw like an imaginary horizontal line, and that means that angle with the imaginary horizontal line is like 25 degrees, right? By the alternate interior angles theorem, then that angle is also 25 degrees. So I can find the direction of this vector just by doing 360 minus 25. Okay. Do we know anything about the length of this vector? No, right? So we get to pick the length. What do you suppose we should pick the length to be? 1. Great. I love it. Has to be non-zero. The easiest non-zero number to work with is 1. So I can then take my vector H and resolve it into component forms. Everybody okay there? Next, I'm going to draw a vector for Kyle and the sled. What force is acting on something with mass? Gravity. Which way does gravity pull? Down. So this is my vector for Kyle and the sled. So what is the direction for Kyle? It's 270 degrees, right? And what is the magnitude of that vector going to be? It's going to be the mass of Kyle and the sled. So doing the same thing. We get 0, negative 165. Now we want the amount of force going down the hill. So what I want to do is I want to project Kyle's force onto the hill. Everybody okay there? Thank you. You are correct. So when I do that, then my projection is just 69.73 times my vector 0.906 comma negative 0.423. And when I do that scalar multiplication, I get this. And the force then that we're interested in is just going to be the projection or the magnitude of that projection. Which comes out to be about 69.73 pounds. Does that number look familiar?
May I have your attention as we come to the end of the school day? Let's stop everything else as we call upon our God, the Father, the Son, and the Holy Spirit. Amen. Do I offer to help other people before being asked? Do I volunteer? Have I begun or completed my Christian service learning?
Shh, I'm not done yet.
Lord God, help me to put my faith and love into action, into service. In the name of the Father, and of the Son, and of the Holy Spirit. Amen.
So, between now and next time, I want you, while doing the homework, to think about when this is true, the magnitude of the projection being the same as the dot product. And I'd like you guys to do 41 through 46.